Hello, everyone. I will continue the discussion of counting with going through some more interesting counting examples uh, using the same two rules we learned before, namely the sum rule and the product rule. And I will talk about some other simple theorems that we can use to do counting. How many beta strings of length n start with a 1 and end with 2, or end with 2 zeros? Sorry, here we want or, so let me just change this to or. The question asks how many beta strings start with a 1 or end with 2 zeros. So recall that beta string is a sequence of 0 ones that you just put one after another like this. And now the question asks to count those sequences with n not digits such that with n bits where they start with a 1 at the beginning and then continue, or they end with 2 zeros. We now do something very similar to what we did in all of the previous examples, and I will draw my favorite sequences of cells. Okay. Now, what we want to count, so these are n positions for all of the bits, and you know that there are 2 to the n many beta strings of length n. Now, we want to count those which have a 1 in the first place, or they have 2 zeros in the last two places. So let us first define two sets. So I define A1 to be set of strings, mean beta strings of length n, that start the 1. And let A2 be set of strings length n that end with 2 zeros. Now, what is the set that we want to count its elements? So obviously, by the definition, is the union of A1 union A2. So we want to count how many objects are in the set A1 union A2. Now recall that we had a theorem from before. Sorry, so I should draw a nice line here. So let me recall that theorem, small theorem. Let A, B be finite sets, then the cardinality of A union B equals the cardinality of A plus the cardinality of B minus the cardinality of intersection. It says that the number of elements, so these are finite states, right? So the number of elements which are in A or B equal the number of elements of A plus number of elements of B minus the number of elements which are in both of them. And the proof of this fact is very simple, as I mentioned once in the class. I now say it again here, so let me do it in this area. And let us have two cells, A and B. And the elements which are in A are in this area, and the elements which are in B are in this area. And if we add the total number of elements which are in A with total number of elements which are in B, we have counted the elements which are in the intersection twice. And if we remove the number of elements which are in the intersection, then we have counted those correctly once, and we get this formula. And now if we just use this formula in our example here, we will get that this number is equal to the side number of objects in A1, elements in A1, number of elements in A2, minus the number of elements in A1 intersection A2. Okay, but these are very simple. The number of elements in A1, because A1 is the set of strings with a start with 1, so we have n minus 1 free places that we can put anything in them, and therefore we get 2 to the n minus 1. Again, the number of elements in A2 are those strings we have two zeros at the end, but we have then n minus 2 places which we are free to put anything that we want, and we get 2 to the n minus 2 as the size of elements in A2, and A1 intersection A2 is those strings which have a 1 in the first place and have two zeros in the last two places. Therefore, we have only n minus 3 places in the middle to put anything that we want, and we can put anything that we want there. And therefore, the size of that is actually 2 to the n minus 3. Therefore, we obtain the number of elements that the uh, example asks. Your book calls this theorem here the subtraction rule, but you don't need to remember any name for this because it's just a simple uh, relation, and it's also a special case of a theorem or a principle which is a theorem. It's called the inclusion exclusion principle. So when you extend this, instead of two sets, you take n sets, then you get a formula which is just an extension of this formula. If you remove all and add a lot of things to count everything just once, and you will get a very big formula, and that is called the inclusion exclusion principle. And here we have only two sets, and the formula that we get is very simple. Let's see another example which has a special property. How many different ways is there to seat four people around the circular table, where we consider two ways of seating to be the same if each person has the same two other persons on its left and right. So let's first clarify what the question asks. The question asks how many different ways is there for seating four people around a circular table, and it has defined what it means by to be different. And it says if a person has the same two persons, we call it around on both left and right, then we say that the two situations are the same. So let's see an instance of that. Okay, so this is our circular table here. And let's have four persons, A, B, C, D. And let's say that we have a person here, we have a person here, and we have a person here, and we have a person here. And now you see that A has B on his left and has D on his right, and B has A to his right, has C to the left, and etc. Now let's take another instance. Another configuration or another way of seating people there. And I will now put A here, and I put B here, and I put C here, and I put D here. These two are now different from each other because A here has B to its left, where here uh, B appears to the right of A. So these two configurations are different. Now let's see an example where they are the same. So if we now put like D here and C here and B here, we just get the same configuration, right? Because everyone has the same two persons around on its left and right. I just started with A and just went through the same order around here to draw these people. All right, now let's count how many different such seatings exist. Where we say different when like these two, we count the same. We say different when this different. Okay, now let's again consider the same situation as before. I mean, consider we have positions to place people. Let me erase these. All right. So we have four positions. Now they are kind of circular. And how many people we can put in the first place? So let's say we put A here. But there are four choices for this cell because there's no restriction on it. This is the first person that we want to see. Now we want to put someone else here, but we have put someone already in the first cell. So this is our first cell, that we go like this. This is our second cell, this is third cell, fourth cell. So we set someone in the first set, and we have four possibilities for that. and we sit someone in the second set, and we have three possibilities for that. And we sit someone else in the third place, and we have two, and we sit someone in the fourth place, and we have only one possibility. So by now we have 4 times 3 times 2 times 1, 4 factorial, different possibilities of sitting people around the table by the multiplication rule. But observe that not all of these correspond to different seatings by the definition. Because if we had started with something else, because it doesn't matter if you start with A, or you start with B, or you start with C, or you start with D in the first one, you will get the same circular ordering of people around the table, right? So let's see, we had A. So let's see, we have chosen A here, we have chosen C, D, E. But this, uh, we could also get the same ordering by placing instead C here, right? A here, D here, E here, and A here. Now you see that the blue here is a rotation of the black one, and but we have counted it still, and therefore we have
Four,
counted
count.
each sitting 4 times, and for that reason we have to now to count the number of sittings only once, because we now have counted them, each of them 4 times. We need to just divide by 4. So the answer will be, sorry, 4 factorial divided by 4, which is 3 times 2 times 1, which is 6. Here we have used some rule or some technique that your book calls the division rule, but I don't want to give any names to it anyway. And it says that if you want to count, if you count objects of A, of a set A, say k times, then you need to divide by k to obtain of to, let's say, count the elements of A. So I read it again. So it says that you have counted, you're trying to count the elements in some subset A, and by some method you have counted each one of those elements k times, and then the total number that you have obtained you have to divide by k to uh, get the actual number of elements of the set A. Here our set A, which we want to count, is the total number of possible seatings of people around the table, where each two settings are the same if the people have the same left and right person around them. under both sides, and we saw that if we count now, instead of that, we count just the different possibilities in these four squares. We actually have counted each different settings 4 times, and therefore to get the number of different settings, we have to divide by 4. The next topic in counting I want to discuss is the very famous pigeonhole principle. This is, most of you know, is a very simple principle that we can write it as the following theorem. Let k be a positive integer, which means greater than 0, if we place k plus 1 objects into k boxes, one box gets 2 objects. This is the most basic form of the pigeonhole principle, and it's really trivial, right? So the name comes by imagining that the objects are pigeons and they have k nests, and if there are k plus 1 pigeons, they go into k nests or k pigeonholes, then there has to be one pigeonhole with 2 pigeons in it. So it's a very obvious fact, and you have seen it before. So let's have now, let's say these are our objects. Let's have 4 objects, or let's have 5 objects, and let's have 4 places. Then let's put these objects into their places. All right, so I put this object into one place, put another object into this one, so when each box contains exactly one object, we have then k objects. Therefore, to add the k plus first object, we need to put 2 into 1. Therefore, the last one now has to go with some of these things from before. Let's see. Okay, this is the very basic pigeonhole principle. Let's now deduce some corollary of this theorem. Actually, this is so simple, people don't call it usually a theorem, and that's why it's called a principle, which means that it has to be intuitively obvious that this is true, and so it doesn't need a proof. And I don't prove it, although what I did is just a proof. You prove by contradiction in a simple way. And a corollary of this theorem, so you recall that corollary means a simple consequence of another theorem, is that no function from a set with k plus 1 elements to a set to elements can be 1 to 1, right? Because obviously it has k plus 1 elements in its domain that it has to send into k elements. So therefore it has to cover at least one element twice, which means that one element in its codomain is the image of more than one element, and therefore it cannot be 1 to 1. You saw that the pigeonhole principle is a very simple principle, and but it actually has many interesting applications, and I want to show you now some very nice example from your book. All right. So let us prove that for any given positive integer n, there is a number consisted of all ones and zeros. These numbers are of the form like 1 1 0 0 and 0 1 1 0, and these numbers are consisted of ones and zeros. Take n plus 1 different numbers consisted of all digits 1. Then now observe that when we divide these numbers by n, each of these numbers has a remainder. Now since we have n plus 1 numbers and the remainders of n, which are non-zero, are only n, if because the possible remainders of division by n are 1, 2, all the way through n minus 1, correct? And these are n. If there was already a 1 with remainder 0, then we had found what we wanted. And therefore, we exclude 0, and we see that there are n reminders. But we have chosen n plus 1 different numbers, and therefore, by the pigeonhole principle, it has to be that two of these numbers that we have chosen have the same reminder. So let's say mm, A1, therefore, and A2 have the same remainder. Now consider the number. So let's assume that without loss of generality, A1 is greater than A2. then consider the number a1 minus a2. Now this number, when it's divided by n, because both of them have the same remainder, the remainder will cancel out, and then it's divisible by n. And this is the number we were looking for. And it has the form that the question asks. I hope this was interesting, and I finished this session with this example.